Alright, so in this problem we have a box P, which is given a prescribed displacement of xb of t is equal to b times sine of omega t. And we're asked to find the two values of the excitation frequency omega for which the amplitude of the forced response of the block A is twice that of block B. And so the way we're going to do this is we're going to start by drawing a free body diagram of block A. And if I do that, noting that x is positive to the right, I can write this as mx double dot, and if I actually do my forces now, I can make an assumption about the relative magnitude of x and xb. This assumption doesn't need to be correct, we simply need to be consistent. If we assume here for a second that x is greater than xb, then what I can say is that the force pulling back here is going to be of magnitude x minus xb. And if I use similar logic, I'll have that the force on the front side will also be quantity k times x minus xb. If I then sum forces in the x direction on this system, noting that the force's weight and the normal force are perpendicular to that direction, and I assume rightward positive to be consistent with the diagram, I'll have that's equal to mx double dot. This result's going to give me that minus 2k times quantity x minus xb is equal to mx double dot, which if I rewrite in standard form is going to give me that m times x double dot plus 2kx is equal to 2 times k times xb. If I then substitute in the value from xb given above, I'm going to have that's equal to 2 times k times little b times the sine of omega times t. And that'll be the equation of motion for the system. Now once I have that, I can go ahead and find the particular solution because that'll be necessary to solve the problem for which we're asked. So in this end, I'm going to say xp of t is some unknown constant a times the cosine of omega t plus some known unknown b times the sine of omega t. I can take two derivatives of that, and that's going to give me that xp double dot of t is going to equal minus a times omega squared times the cosine of omega t minus b times omega squared times the sine of omega t. If I then take both of these results and substitute it back into the equation of motion, I'll have m times quantity minus a omega squared times the cosine of omega t minus b times omega squared times the sine of omega t, not omega k, omega t, sorry about that, plus 2k times quantity a times the cosine of omega t plus b times the sine of omega t is going to equal, in this case, 2k times little b times the sine of omega t. Now that I have that, I can separate out distinct trigonometric functions, and if I do that, first of all, looking at terms multiplying cosine of omega t, I'll have that minus m times a times omega squared plus 2 times k times a is equal to 0, which of course gives me the result that capital A has to equal 0. And if I look at terms multiplying sine omega t, I'll have minus m times b times omega squared plus 2 times k times capital B is equal to 2 times k times little b. If I solve this for capital B, I'll have capital B is equal to 2 times k times little b divided by quantity 2k minus m omega squared. I can take this result now and say that what this means is that, let me do that one more time here, that x sub p of t is going to be 2k little b divided by 2k minus m omega squared times the sine of omega t. Now in the problem statement we want to find the frequency values, that is the excitation frequency values, for which the amplitude of the response, that is capital B, is equal to twice the base excitation. So what we want to find here is the case where 2b, twice the base excitation, is equal to the amplitude of xp of t, which is 2 times k times little b divided by quantity 2k minus m omega squared. This can be true under two conditions. Condition 1 is where 2b is equal to 2kb divided by, 2k minus m omega squared, as well as the case where 2b is equal to minus 2kb divided by 2k minus m omega squared. Let's call these cases case 1 and case 2 respectively. If I go ahead and solve case 1 for the excitation frequency, I'll get the following. I'll get that 2b is equal to 2kb divided by 2k minus m omega squared. I can cancel out the 2b that appears on both sides, and this gives me that 2k minus m omega squared has to equal, in this case, little k. I can write this and solve this equation and get that k then has to be m omega squared, which tells me that omega can be plus or minus the square root of k over m. In this case, we typically only take positive frequencies in this class, and so we'll simply say that omega is equal to the square root of k over m. If I look at case 2, I'm going to have that 2b is equal to minus 2kb divided by 2k minus m omega squared. I can again cross out a 2b top and bottom, and in this case I'll get that 2k minus m omega squared is equal to minus k. In this case I'm going to have that 3k is equal to m omega squared, which gives me that omega is again plus or minus, keeping only the plus, 3k square root of 3k over m. And these will be the two frequencies at which the system exhibits a response which is exactly twice that of its base excitation. I'll leave it up to you to finish up from here. I wish you the best of luck as you do so.